Okay, folks, I think we'll go ahead and get started. It's good to see you all. I'm really looking forward to sharing some more details here. Let me go ahead and open up in prayer, and I'll give you a little bit of a table of contents of what I'd like to have us focus on today. Dear Heavenly Father, Lord, I pray that you would be helping each of the students in this course. Lord, I pray the material will be clear, that they can see that it's enjoyable, and something that they're going to be able to utilize as they go forward from here. I also pray that you would continue to help them in their journey of spiritual formation, to just getting a chance to be guided through scripture, to learn the theological concepts that we want to be um, directing our life by through people that have been invested in that and the various classes that they're doing that, so that when they leave APU, that these are things that they're going to be able to activate and continue to use all of their life, and that they can have some interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Well, like I said, the focus on Thursdays is meant to be kind of like a lab. So maybe if you were to pretend like this is a class where you have a lab session and Thursdays are our labs. And so I'll just give a little bit of a review on a couple things, just thinking about where we are in our journey through our textbook. And so we've talked about the basic concepts of computer evolution. It's amazing to think like an IBM 370, how you'd have to program there. And so how easy and accessible a lot of computing capability is today. We talked about very high level performance concepts and something like gigaflops. There's different ways in which you can be measuring performance that probably aren't the best way. And so in chapter 2, we got a chance to talk about more effective ways to be able to have an apples to apples comparison. Then we started to be looking at the computer function and interconnections. Interesting enough to think that a computer, maybe a way to be thinking about it is going beyond the hardware per se, of what actually are we trying to accomplish. So if we're doing it with gears, if we're doing it with vacuum tubes, if we're doing it with microelectronics, transistors, all of those are just examples of implementations of where we're going. So we're going to be continuing to go through this process of thinking through the computer system at a higher level, but we're also going to be diving into some stuff that we'll get into more details here when we think of like arithmetic and logic. And so we're actually doing some stuff with our first sub-project, thinking about digital logic. So keep that in mind. So a couple of the things, I'll just pull up Canvas to remind you of some of this information. So where are we at in terms of the things that we have available to us in Canvas? So I would recommend, if you don't have Canvas open, go ahead and do that. I'm going to highlight a few things here. First of all, under the project resource information page, there's a couple tabs that have videos, and so this is more focused on helping you get started with the resources. And I think everybody has your digital logic simulator up and running. Last Thursday we got a chance to get that working, so that's the first thing we'll talk about. Also, at a request of one of the students, I got a request to get a little bit of a heads up for the second one, to be thinking about how we would actually program an assembly language. And so this is the link to install that. So please take advantage of that. And I also put up a sample assembly language program called Hello World. And so I'll walk through that in class today to give you some more ideas about that. And then for the third project, this is the Arduino microcontroller. This is the link that I want you to be aware of. It's also in the syllabus. And so if you just click on this, it'll just take you to a representative starter kit. So something like this kind of level of complexity, even with the fact that it has an LED display, I think that's a little bit overkill for what we need. But I would recommend that you get those kits as soon as possible. And just to give you just an idea of what that looks like, I'll stop sharing my screen for a second. So this is probably the size of a kit that you're going to be getting. I got this a couple years ago. And so by now I've kind of been moving things around a lot, but eventually what you're going to have is you're going to have something like this. And so this little thing, this is called the Arduino, and there's various manufacturers. And so this is a wiring board here, and I have a bunch of wires and things here that I'll be showing you. There's an LED, and this is actually has a light sensor on it that is kind of cool, and it gives you an idea of a representation of the things that we'll be doing. You're going to be plugging that into your computer with a USB connector. Last year, I actually got had students get a larger kit. This is probably too much, but why I'm saying too much is I want you to be able to be thinking about how can you do a demonstration of a capability with limited resources. And so it's more of an engineering / computer science exercise of thinking about that. What is the most important thing that I need to try and do with that? And so I mentioned, as I've had discussions with individuals and as it's come up, like, well, what do we need to put in the project proposal? And then how would I do that implementation? I want to be there to help you do that. And so it's actually going to be hopefully not so daunting with us spending some of our lab time to go over some of that information. So that's a little bit of a show and tell. I was looking for some of my stash of hardware, and I don't know if I'll be bringing this into APU, but just to give you an idea, this is like one of those cards that you can stick into a computer. And so you have your motherboard here, you would stick this in down here, and then you have various things that you would be connecting to the input and output. And you might have been able to see this as an AverMedia Ultra TV. One of the things that I had fun was how you could actually watch and record over-the-air programming on your TV. And so this is something that I haven't played with for a while, because as you probably might be aware, the over-the-air transmission have changed. Now it's gone to a digital format, which instead of an analog format, even for the regular over-the-air stations. And so for a while you had to get the special adapter. Now it's just built in the TVs, and you kind of forget about that. That's just sort of the status quo. But anyway, that's just a little bit of an idea of what's going to happen a little bit towards the middle of our course, when we start to be thinking about how we do this cyber physical type of an environment. But go ahead and get your kit now, because you can start to be bringing that in on Tuesdays, and we can be talking about that together as a class, and I can be trying to clear up any things that might be confusing for you, because it literally, just by how do you actually plug a wire into that white thing that I was showing you, that's something that you want to have a little bit of time to get some perspective on that. So let me just verify, are you guys seeing my screen again? Because I was turning things on and off. So thumbs up, thumbs.
Yes.
Okay, good.
Yes.
So this is going to be an important tab that you want to be mindful of. So the quizzes are stuff that you can submit. There's a schedule, and so let's go back to the syllabus tab for a minute. So the syllabus shows up, but if you scroll down, and you should see it when you go into Canvas, the due dates. And so for today, September 7th, you have 2 quizzes that are due. And so, and also the project proposal. So I'm looking forward to getting a chance to be seeing some of the things that you have, that you would like to be doing. And so that's going to be this first thing, is just trying to give you think big. What is the big picture? And then have a few thoughts of what you might want to be doing for each of those sub projects. The next thing after you do that, you're going to be having these various assignments that you're going to be doing. And so let me just give you an idea. I'll go into student view. And so there's a little narrative of what you are wanting to do. And there's also a rubrics here to give you an idea. And so you can see that what I would like is for each of these sub-projects, you're going to do 3. So for the first one, you're going to have 3 digital logic designs that you'll submit. And one of the ways I try to make it so people would see it's not as difficult as what that might sound, is because you can have one and then you can build a little bit onto that and then build a little bit more onto that. I'll show you an example of where I was actually using this for some of my research. Maybe that'll give you some insight. And then there's other kind of factors that I was looking at that are there. And there's a variety of different types of things that you can do. So what I'm looking for is you have a summary document, and then you can have like your scripts. And I think for the digital logic simulator, each when you save it, it has a .dig. That's the way that it's saved in that format. ASM is for the assembly language. That's the format that I'll also get a chance to share a little bit today, and just some other types of things that you'll be doing. So that's something that you guys can be looking forward to as that comes up in the near future. Any questions on that? Okay, I'm hoping that would be fairly straightforward. And also, like I said, I'm the instructor, but maybe I'm also the coach, if you will, or a mentor. So like I said, when you're trying to think of your project proposal, I want to be here to give you some insight into that. So that's going to continue on as we go. All right, well, let's next go to the digital logic, but maybe if you have a little bit of time while we're chatting here, make sure that you download and install the Mars program. This is what we do for the assembly language, because I'm going to talk about this after we're done going over a little bit more in the digital logic. So this is one that I showed last time. This is another one that I had that I'll just give you an idea of what this is doing. This is just simply a AND gate. And so most of this I've already talked about, but then there's a couple ways that you can be showing information. This is one of those ways. And so if I start to go on to execute, what these little lines are doing, this is something else you can do. Just it gives you well, what is this from a logical faction? So 0 or 1, if we were thinking, some of you guys are engineering, and so you could be thinking this in terms of voltage, 0 and 5 volts. Transistor logic, TTL, that has been a term that's been around for a while. That was how this was originally envisioned. Sometimes you're not actually going from 0 to 5 volts. It could be they're doing things at a lower level, like 0 to 3.3, whatever. But I'm just going to use that as a general term. And so this is now activated. And so if I click on A, this is going to be like with your Arduino kit. You're going to have those physical buttons. And so you can be thinking of this is like on your Arduino kit. And you even like that white wiring board. This is kind of, you could think of this as like all these little things here. If this was that white wiring board, you could stick a wire in there. And I'll be talking a little bit later how multiple ones of those things are actually hooked together in the back. So instead of like soldering things together, you just stick them into that wiring board, and it's a lot easier to use. So you can see how that went from 0 to 1. And this is like an oscilloscope that is giving you an idea of what the inputs are and what the outputs are in a graph. So let's go ahead and click this other one on. And I also put an LED. That's something else that you'll have the ability to do in your Arduino kit. And this gives you a little bit more insight that what's going on. This form of a scope is limited, that when it gets past the end of this page, it's going to continue to do things, but you're not going to see it. But that's at least one type of scope that you can be thinking about. We initially just talked about a 2 AND gate, and we started to walk through this last time. And let me see if I can. I think I had an and and an and. this is all my recent ones, and I think it's that one's fallen off the list, so I may not resurrect that right now. So let me just go around the virtual room. Has everybody got at least one of their digital logic designs complete that you would like to use for your project? So literally what I'm saying by that question, I didn't want to make you gasp or anything, but this is like an example that could be for one of your first circuit. Okay, so I just want to give you a perspective what I mean by that. But what this is not having is what you are starting to do with your project proposal. Well, what does this mean? And so why would you want to be having a truth table that's going to have this kind of a result? And I know last time I was having some difficulties having this work. So let me see if it works. No, this is the one that for whatever reason, it wasn't working. So let me just close this one out and open another one. So okay, let's try this one. This one should work. So what happens when I go like that if it's changes? Yeah, I'm not quite sure why that's not working. But anyway, this is one that I talked about. This could be representative of like you're having three things that are added together. And so the only way that you're going, sorry, I'm going to go into run mode. So the only way you'll get a positive is if you have the two inputs activated, and you can be just sticking in an LED to give you a more better way of seeing that. And here is another example of what that could look like. So this is something that you could then build upon. I'll show you something that I did for some of the research that I did. I actually, because of what I was trying to accomplish, I migrated to a different tool. But this was something that I was trying to look at with some of the research I've been looking at, is that bacteria, there's a way that it senses where the food is and where the things it wants to get away from, and that's called chemotaxis. And so I was looking at chemotaxis control. And so there's three things that it happens. You can think of like your nose or your mouth, and so you actually can sense something. So you probably, maybe you've had like every once in a while we smell something in our home, and is like, is it smoke? You want to figure out, well, hopefully it's not coming in somewhere in your house. You kind of using your nose as it's guiding you where you want to go to try and figure out where that smell is. Well, that's what this first thing is. There's this way that it's done for a bacteria, that it senses how things are working. Another thing is, well, how does it pass that information? It's not using electricity. And so there's another mechanism that actually does that signaling of passing that information on. And finally, it has a way of adapting to the concentration. Maybe you've experienced, like if you've been in a loud room, that your ears start to adapt to that loud noise. And say like you walk out of that room, your ears are in a point where it's so used to that loud noise, it's like you'd have to wait for your ears to settle down. Your eyes do the same thing. They start to adjust to either low light or high light situation. So that's what this is trying to show. And so I was just trying to look at some of the control logic for that, of what it would mean. So first of all, let's say that you're saying, okay, now I'm going to sniff. And the other thing that I'm doing is, okay, now that something is there that I'm sniffing for, that I detected. And so this is a different type of scope, that whenever there's something for it to detect that there's changes, it's actually clicks on. So that's the reason why you just saw that come on now. So that's the first part of it. The second part is, well, now for this signal to propagate, it has to go through all of these things that propagates through that. Okay, that's the first thing. So it knows that there's something to sense, and now it's starting that signaling path. Okay, and it says, the next one says, okay, Okay, now I'm going to follow suit, and so it activates that. And finally, it gets to this third point, and now I have these multiple scopes that start to show up, and they just popped up because I got to a point where something was activating in those areas. And so that was like the first way of how I was looking at thinking of maybe something that is complicated, but just trying to give you an example. This might be overkill for what you're trying to do, but you can be just thinking about that. So that's the first one I came up with. And then the second one, I started to make some added some sophistication. So this is going to be staying the same, but I'm going to add stuff to it. And this is what I mean for your digital logic, you can build on one another. So I had the same smelling detection, if you will, the same signaling path. Now what I was trying to do is to see how I could add some sophistication that would be showing some of this adaptation that I mentioned an example for smell, and that I mean for what you would hear or your sensing with your eyes. And so if I was to activate this, what this is I actually put in a clock. And so what this means is this it just kind of automates this whole process and has things starting to go forward. And this was my first attempt at trying to not only have those two other mechanisms, but having a third mechanism, and I added that complexity to this kind of a circuit. So I'll stop that, and then I'll go to the third one. And so that one didn't quite work the way I'd wanted. And so then I implemented it this way. And so instead of having the clock be part of the input detection, it was now part of the signaling path is where I stuck the clock. And so this is where we have here. And so because now what this is doing is just saying that the clock is ready if you wanted to do it. And so this is another thing that it's not really something that we need to be talking about in this, but it is something that's available to you if you wanted to be using a clock. So at this point, there's nothing for it to clock. There's nothing for it to pass on to signal because there is no input. So let's activate. So now it's able to sense. And so, but there isn't anything that it has sensed so far. So if I activate, okay, now something that is sensing, now it's passed on. Okay, this is what I want to be doing. And so that is actually a good thing. And so now that we have that, then I need to start this process of doing this signaling. So I just have this set up as manual inputs. Okay, now that I have all three of these things are activated, that's what's there. And it's a little bit hard to see, but this methylation is when it actually counts up to 4. There's sort of a dynamic range I'm trying to be thinking about it. When it reaches that 4, it says, okay, it resets it. We need to start over. And so that was where I went with this digital logic design to give you an idea of some of the things that you can do. Any questions on that? I know the application isn't something that you're doing, but maybe it's something for you, an idea for you to be thinking of how am I going to start with something fairly simple in terms of something as simple as this, just a couple of AND gates, and then you're trying to provide the meaning that's related to what's important to you or what you're trying to accomplish with your setup. Okay, so start with this. Maybe that's what you're beginning to have. Maybe then you would start to get something a little bit more complicated. This is an example of a circuit that is a little bit more complicated. I think this one should show properly. So let me see if it, I'm not sure why. Well, anyway, I'll just have to look in that. That's kind of an aside for now. And so this is using some gates that we haven't talked about in general, in detail, but we've sort of seen this a little bit here. So anybody remember what this is called?
Not gate.
Yeah, it's a NOT. You can also be calling it an inverter. So basically, let me activate this. So whatever's on the input, it does the reverse of that. Okay, and so this little circle is indicative of something that we'll be using here. So let's pretend that this doesn't have a dot in there. What would this be called?
AND gate.
Yeah, an AND gate. And so what they call this, you just stick an N in front of it, and they called it a NAND gate. This is an OR gate, but you stick this in front of it, and then it's called a NOR gate. So basically what this means is, well, let's just kind of look at this. So I'll turn this one off, and so it's getting a positive input there, but nothing's coming out. An OR gate would do that. And so the only time that it's going to actually turn on is if both inputs are zero, logical zero, or 0 volts, however you want to be looking at it. And so those are just a couple other things that we're seeing there, just to give you an idea. So this, you can see the reason why this scope came on was this is the first time it had a positive change on the output. Otherwise, this wouldn't have turned on. And so, but now that it's clicked on, then I could be seeing all of the different changes that I have going on with your inputs. So those are a couple examples of what you can be doing with your digital logic emulator. Okay, any questions on the digital logic emulator? Anybody have one that you'd like to show, even if it's just a one gate, if you just want to share? Okay, well, we'll leave that for now. So that's the first one that I wanted to have you continue to be thinking about. Next, let's talk about the assembly language program. So does everybody have this installed? And if not, it's similar to what we have for the digital logic simulator. And I also validated that both of these work both on a Mac and a PC. And maybe what I'll do is I'll show you this. So let me pull up a virtual machine. I actually it's give me 1 second. I need to configure something. Maybe while I'm doing that, if you guys want to try and download that emulator, and then I'll remind you how to do the installation for that. Anybody heard the term DHCP? Dynamic assignment of IP addresses?
No.
So my router, what it did is it gave a different address for this other machine that I'm using. And so maybe some of you guys like cats. This is one of our cats. So some of you guys but anyway, he's kind of showing himself off there a little bit. So this way I can kind of help you see a view from both a Mac and a PC. And so what I did is for the Java, there's actually an open source JDK that Microsoft makes available. And so the good news is I was able to actually use that and it worked. And so this is that same program. Once I've done that association, it just comes up. One of the things that's kind of cool with this, it actually shows up on the color. And so there's a little bit more of a richer experience with that. But that aside, it works just like the way it does on a Mac. So let me introduce one thing and then I'll switch back over to my Mac. If I just click on the help, this is this really, there's just a lot of things that are underneath the hood. And so it's actually fairly self-contained to give you an idea of what you would be doing. So let's pretend like this is an assembly language, but we're talking about Python or Java. First thing you need to know is what are all the instructions that you can use, and then you need to be thinking about the syntax. With this help menu, this is a way of having you know what that is. And so I'll just go down to this third line. This is like the first of several different types of ads that you can do. So you can do ads, you can do branching. These are the types of things that you would have. So basically, this is the types of things that you can be accomplishing if you're trying to do something in assembly language. Okay, let me go over to mine. And so just as a reminder, so under project resources, this is where you can get that .jar file. I can also just paste it, copied in there that you can download directly from it if anybody has it. So has anybody found where to get the .jar file? Everybody found it? Okay, anybody not found it yet?
I was having a hard time downloading the Mars file. It would save it, but it wouldn't let me open it. It just kept going to like the Internet Explorer.
Okay, well, I won't try doing it real time, but I'll put that in here as well. So let me try something, see if this will work. This might work. I think I might be able to in the chat. Put a file there. So let me try that real quick. And then I can load it later. Okay, it says access to file restricted. Try something. Okay, what I tried, let me see if this works. No, that's not working. Well, I'll do that right after class. I don't want to waste too much time. I apologize. But this is also good feedback. Like I said, I redid the class. And so I'm just trying to find out the best way to share this information so you have it. So I'll put the .jar file, but both for the digital logic as well as the one for the Mars. So anyway, so let's begin to think about this program. And this could be representative of the kind of things that you would want to be doing for what you want to be doing with what you were trying to highlight in your proposal. So let's think about that. You guys are probably familiar with the concept of a program called Hello World. Just about every programming language, they'll kind of show you how to do that. And so this is a way of how you would do that in assembly language. So we're going to get into this, but now this will be sort of a first encounter to me thinking about what an ARM type of processor. So that is a reduced instruction set. All of the instructions are the same length. We're going to talk about that a little bit later. Instead of doing it that way, you can have variable length. And so everything is at the same number of bits. There's also 32 registers. And so that's what we're showing over here. And you could use up to 32 registers, and they have different type of purposes. And so another thing that I found, I keep finding new things. And so if I just hover on top of this, it'll actually tell you a little bit of insight into what each one of these registers are. And so we can see that it's actually calling up things here like V0. So let me just hover down on find V0 here. V0 is right there. So an expression, evaluation, and results of a function. So we have that. We have A0. A0 is right there. It's argument 1. And so these are just some of the things that are there. Another characteristic of assembly language is you have a lot of comments, because this is not very intuitive, but based on what you're trying to do, it actually works pretty well. You can have like here, you can have like branches, and so or here you have like you have a variable, and so you're declaring what it's going to be. So this is a director. So the directives, and so here like the ASCII. So we're seeing that this is an ASCII with a Z, so it's a string in the data segment and add null terminator. So it gives a little bit of description. .text, we have that's here. .global. So these are all the directives that are helping us navigate. It's helping the compiler figure out what it's supposed to do with this information. And so that's what's going on there. So let me see, I think I already did this. So what you would want to do is once you've loaded this program, you go into run, you click assemble, and this is what you're going to get. So this is where it's converting this into ones and zeros, the way that this processor is designed to figure out how to do this. And what you'll notice is sometimes it would put in more steps, sometimes maybe not. So you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And so this is an example when something is broken up into more than one step to make that work. Okay, so I can either just run it and it would just show hello world, but another thing I can do is I can go into single step mode. And so here it's ready to execute this first line. And so what is this? It's adding. So let's go back to this help. So this is an add IU, addition immediate, unsigned without overflow. These are all some terms that we're going to get a chance to understand as we get into this in more details. So addition immediate unsigned without overflow sets at $sign T1 to well, anyway, you can read the rest of that there, but this gives you a little bit of insight of what's going on. So let's go ahead and just do single step there and see what happens as we look at what's going on in these registers. Okay, might be a little bit hard to read, but actually there's a 4 here, so it stuck a 4 into V0. That's what that first thing did. And so this is the code for a syscall. And so this is another thing that, you know, this is a very low level kind of communication. What you're trying to do is to have the syscall print out a message, and this is the next thing that it's going to do. So it's going to, okay, this is what I'm supposed to do. And then it's going, you need to tell it, well, what is the information that you're going to do with that syscall? And then you actually execute the syscall. Then you do a termination for a ending. Like if anybody has ever done command line programming, like int 0, it's one of the ways of how you can, if you have something in Unix or Linux, if you were trying to turn off the machine, you could be, that's so something that's kind of like what's going on here. So we're in the main. First thing we do is we want to be passing on the information, telling the processor that we want to have something that's printed to the console. We have that. And so that's the first thing that we have laid out. So let's do this next command here. So I think this is where this might be useful to click over. So we're actually looking at some of the memory here. And so you can see that we know from over here that this is, we're trying to print out as hello world. And this \n, this is a carriage return. So those are things that we want to be making sure that we do. But look what we have here. You can see that this is now in the way that it's configured for the processor as HELLO space WORLD exclamation mark, and then we have this \n. So that is another ASCII character, but there's if we wanted to represent that so we're not ambiguous, we don't want to be thinking that's an N, this is the way how we would be doing that. So that's the second command that we did. And so now it's ready. Now we could actually do this next step. So let's look that up. ORI. Okay, this is a bitwise or immediate set. It's just another one of the commands. And so this is one of those things that in our original program, it's kind of not there, but this is like, has to go to a step lower level to be able to be ready to do a syscall. So that's what that one is doing. So I'll just go ahead and execute that. So I don't know if I can go back, but anyway, so and then if I do this next command, I should have this appear down here that we'll see the hello world. And so we get the hello world printout. And then we're just trying to make sure that we end this program in a clean manner. And so then we just do another syscall. This is the code. This is the code 4 was to print to the console. The one for to exit is 10, and so we're set up to do that. Then we go ahead and set up that information that it's going to act upon. So your load, it's like, it's a low level, so all it knows is it communicates with the registers. So if it needs to do something, it has to go to the registers, get the information, and then activate that what you're to do. So sometimes there's a few more steps than what you're familiar with. And finally, we get a nice program that's finished running, and so you get a nice clean exit. So any questions on that? So just by show of hands, David, I know we're still gonna get you up to speed. Anybody else having problems? Anyone else have issues getting it downloaded and running in their computer? So please reach out to me if you did, and I'll want to make sure that you get started on that. And so maybe it's a first program, we're just showing this engagement with registers and stuff like that. Think about how that might work. Maybe a more complicated thing would be how you would add things together. And I can be showing you a couple examples of that. Say like I have like a Fibonacci program, a couple other types of things that we could talk about. But for now, I just wanted to give a first blush, having you think about that, and then we can move on to some other things. So any other questions related to the digital logic, or this was a first blush look at what you're going to be doing with the assembly language? Let me make sure I got the chat. Sometimes it sticks it in different places, and so. Oh, Austin got it to work. Avery, good. So seeing a lot of folks are giving some positive feedback. That's really good news. And I'll continue to help the rest of you. So the good news, and I've actually spoken with the developers of this, it's getting a little bit dated. And so I'm always thankful if I install a new version of Java and it still works, because every time I look at it, it's got more things under the hood. So for educational purposes, it's great. It's not like the latest processor or something like that, but it's representative of the kind of thing that we want to be doing in this class, to have people have an idea of what a processor is actually doing at a low level in a way that it's user friendly. And I was just trying to highlight a couple features that you could get a chance to be taking that raw information and actually get a chance to be viewing it in a way that's easier for us to understand. So those are pretty much the highlights of what I wanted to be thinking about there. Since this has come up a lot, maybe I'll just take this moment to see, does anybody have that would like to talk about their project proposal? I could walk you through the handful of questions I've been working through with others, but I could help you if you're still trying to flesh out those details. And so what I usually start out with is, if you're haven't come up with an idea yet, what are you interested in? Both thinking about what you would like to do with computer science or engineering, and other interests. Like the last time I was speaking with and Josiah was who I was doing that with, and he is into soccer, and so I was trying to give in of how he could adapt it in an area of something that he found interesting. Cybersecurity, movies, video games. There's all kinds of things that you can be doing to be thinking about how you could apply this. And then we're going to try and do some risk reduction and thinking of how we would actually make a cyber physical capability that would be helping us to do something in those areas. And we'll have 3 modalities to work through that. Okay. So I'll just pause and see if anybody wants to talk about that. Riley, I think you were the one that wanted to get a heads up on the assembly language. Did that help you fill in a couple of the gaps there to give you a path forward to get more familiar with what we're doing on that front?
Yeah, definitely. No, that helps.
Okay, good. Well, we'll continue to work on that, but like I said, Thursdays are going to be more the day of us roll up our sleeves. You can learn things by just reading a textbook and taking quizzes, but sometimes that can be kind of dry. And so hopefully on Thursday, we can have another way of getting some access to this material, and we'll continue along that thrust. All right, I'll just take a few minutes just to go back to the lecture notes and just begin to be thinking about few topics here. We'll focus on the next chapter on Tuesday, but maybe I'll just do a precursor for just about 5 minutes or so, 5 or 10 minutes or so till we're done with our time. So there's just a lot going on in computer architecture. I've been telling you one of the things I've been doing is thinking about neuromorphic computing. And so it's just another architecture, having other kind of things that are a little bit more what you would find in the brain. There had a level of trying to do that with a von Neumann architecture. And so this is another jogger. Anybody remember the 3 things that a von Neumann architecture consists of? By now you probably heard the name. Anyone want to throw out one of those 3 things?
CPU.
There you go, CPU.
Memory.
Yeah. Memory, that's right. Any other daring souls want to say what the 3rd one is? My chat disappeared, so somebody did via chat. I didn't see it. So input and output is the other one. So we've seen that. We talked a little about computer evolution. We haven't really talked in detail about these 2 major classes, the ones that we'll talk about in here. The Intel 86 architecture, and then there's the x86-64. That's the current thing, and then there's the ARM. And so stands for Acorn RISC Machine. So this is like this reduced instruction set versus a complex instruction set. So we'll have like these competing things, complex instruction set, like when I was showing you with the assembly language emulator, everything's a fixed length, 32 bits. Intel, that's not the case. You can have commands that are 32, 64, 128. And so there were reasons why they were thinking that that would be a good thing to do. So we're going to be getting a chance to be considering both of those as we move forward. I was trying to see if I could find a PCIe card, but I wasn't able to find one. I always, my wife especially helps me along when I don't have too much junk, so I have to kind of clean things out a little bit. So I still have my TV card, but some of the old modules I've ended up donating. But this was something that I thought was kind of cool, the way that we do it is you can have a virtual point-to-point connection. And so that's something that we got a chance to be exposed to. One of the topics in chapter 3, one of several. And chapter 4, we thought a little bit about input and outputs and the whole function of a computer. In chapter 3 and chapter 4, we start to be thinking about hierarchy. And so this is where we start to be thinking about a couple of the things that are in the memory side, good news and bad news that are things that we want to be thinking about. So I was trying to allude to the fact with one of the charts that I had in the greatest hits section that you have this, that the way that memory for instructions actually is a little bit different than data. And so there's a little bit more sequential going from thing to thing and instructions, but in data, that's not the case. You can be like all over the place. But still, the way that you're seeing it is just one large contiguous thing. And so the CPU just needs to know where, it doesn't need to know the details that you have 2 or 4 sticks of memory. It just needs to know that what is the address, and when I go there, it consistently gives me the result. And so this is what your motherboard, your system board, your system, it does that translation, and so we get a chance to be thinking about that. So with our assembly language emulator, we're going to get a deeper dive into the CPU. With the Arduino project, we'll get a chance to be seeing how this processor engages with external devices. And so those are the things that we'll get a chance to be thinking about. But we also want to be mindful of the memory. And so that's what we start to explore here. And so that's just a little bit of a high level few thoughts to be thinking about that. So I think that's probably good enough to just to give you a heads up for what's going to be coming on next Thursday. And so anybody want to share what you're going to be doing with your project? Just as a heads up, we also could spend a little bit of our Thursdays to go over that in the next couple of weeks.